Okay, so here's lecture 3. So here we begin again with I just want to show you one property of least squared estimate a little bit. So let's say let's just recall this fact. So y, you have x beta and your sigma squared I n cross n is a linear model. Right. Then we remember we did long time back. You take a vector p in Rm, let's say, and I said the linear parametric function I called it P transpose times beta. I said it's said to be estimable, that is, it's identifiable from the model if what happens if there exists a vector L, right, in Rn such that expected value of L transpose Y was equal to P transpose beta for all beta in R. So I needed this for all beta. So this is what I mean by estimable, right? That's what I read long term. There's other words that you have an unbiased estimate for L transpose Y. Right? So that's I'll just write down an unbiased estimate for L transpose Y. Okay, very good. So I want to show a theorem for least squares with this guy. Let's try and do this. So here's a nice theorem. So let y x beta. I'll take a uncorrelated model, linear model. Linear model, right? And let's say P is in Rm. It's sort of a little unintuitive, but once the proof is there, it's not so bad. P transpose beta is estimable that is, you can find an L for which L transpose Y is unbiased estimate as P transpose beta. This is if and only if its least squared estimate is unique. Its least squared estimate is unique. Its least squared estimate it's kind of a funky, nice idea. So you can only estimate it. You can find an L transpose Y is equal to P transpose beta only if the least square estimate is unique. Okay. So let's try and prove it. Let's try and prove this theorem. Okay, very good. Now suppose, so let's do the only if part. So let's do only if part. So let's suppose P transpose beta is estimable. Right. So what does this mean? This means, so do you remember this? We did a theorem long time back. That means estimable means that P has to be in the column space of X transpose X, right? This is a theorem we did some time back. in the previous class. I don't know if you recall the theorem. Let me just say this from a theorem done before, right? So this from, so recall earlier theorem from Feb 9th, where we said P has to belong to column space of X transpose. Right? This we have done this. Right. So once you have this, P is X transpose, right? That means what? That means there exists a B. So B will be a vector in Rm again. Vectors properly in Rm, such that what happens? X transpose X, I multiply it by B, I should get P. And that's what means by P is in the column space of X transpose X. Right? So this is what it is. So now, suppose, now let's add contradiction. Suppose there are two beta hats, right? That is beta 1 hat and beta 2 hat. Let's say they solve the normal equation. There is what normal equation? X transpose Y, X transpose X beta is equal to X transpose Y. Let's say you have two solutions. Then this would imply, let's call this as we call this dagger, let's say dagger. Then dagger would imply P transpose beta 1 hat, right? But what is P transpose? P transpose beta 1 hat is just X transpose X transpose, and then I have a B transpose on this side, and I have a beta 1 hat. That's the same as B transpose, X transpose symmetric, so I get X transpose X, beta 1 hat. But what is X transpose X beta 1 hat from the normal equations? That is, since they solve normal equations, let's call this as let's say triple dagger. So from triple dagger, so what do I get? That's equal to, so that's equal to B transpose times X transpose Y, right? Everywhere is the Y vector, right? It's vector. Now what is X transpose Y again? From the equation again, I go triple dagger. I go triple dagger again. I reverse it. Beta 2 had a solution. So I write as B transpose X transpose X beta 2 hat. But that's the same as B transpose times X transpose X, so X transpose X, sorry, I should not say. I look at these two together times beta 2 hat, and that's the same as P transpose beta 2 hat. That means the least square estimate for P transpose beta is unique. That is, this is unique, right? It's unique. So that means, therefore, the least square estimate of P transpose beta is unique. Because even if the normal has two solutions, any two solutions, they will give you the same answer. So let me just write this down properly. So suppose beta 1, beta 2 are, let me cut this, are two solutions, are any two solutions on equations, it turns out that P transpose beta will be the same as P transpose beta. Beta 1 hat, same as beta 2 hat. So that's unique. So I've shown this implication. So this implication is done of the proof. Now let's do the reverse implication. Let's assume unique estimator and then show that we have a estimable quantity of P transpose beta. Now here's the initial linear algebra. let's see that works out for you. Suppose that P in Rn is such that the least squared estimate such that the least squared estimate P transpose beta hat, let me say least square estimate of P transpose beta is unique. Suppose I'm here, right? So then what does it mean? That means for any two, so this is the first fact you have. Then what happens then for any two solutions of the normal equations, any two solutions, let's say beta 1 hat and beta 2 hat of the normal equations, what do we know? We know that the P transpose beta 1 hat is the same as P transpose beta 2 hat. And that's what it means by unique. Okay. So now we already know that normal equations are what? X transpose X beta is equal to X transpose Y. That's what the normal equations solution means, right? So now this is a simple exercise to think about. So let's exercise think about. If lambda is such that it's a null space of X transpose X, such that X transpose X lambda is 0. Okay. Suppose lambda is in this space. That is. Then P transpose lambda is also 0. So this is a simple exercise to think about. So I have this equation. So that means, let me write down even a stronger statement. That means for every lambda such that X transpose X lambda is equal to 0. So why I put Y, I'm not sure, equal to 0. So the null space of this, then P transpose lambda has to be 0. That means, so this is simple linear exercise, because all you have to observe is that P transpose beta 1 hat minus beta 2 hat is 0 whenever beta 1 and beta 2 are solutions of the equation. That means for every lambda of this equation, P transpose lambda has to be equal to 0. Simple linear algebra fact to think about. So this implies, what does it imply? That P is orthogonal to lambda transpose. To lambda, sorry, P orthogonal lambda. Right? And lambda was any vector what in the null space of X transpose X. That means P is orthogonal to the null space of X transpose X. But that means what? That means P belongs to the row space of X transpose X. But we know the row space of X transpose X is the same as column space. So P belongs to the column space of X transpose X. Right. So I've used some heavy duty linear algebra to show this thing. Quite cool. So that means there's a kind of nice theorem that is what we have shown is that let me go back and we get this. What we have shown is that if your P transpose beta is estimable, then it better be that its least square estimate is unique. And the proof goes by a very simple idea that so first you take estimable. That means what? That means P is in the column X transpose X. That's because last time we had shown for estimable, P has to be in the column X transpose. It was also there in the homework. That means what? There's a B in Rm, so X transpose X is B. B is B. Now, if you take two solutions, all you have to do is just work out slowly. Right? Look at P transpose beta 1 hat. Beta 1 hat solves normal equations. So if you replace the definition of P as X transpose X times B, you'll get this equation, and this you can replace it by X transpose Y because normal equations. Then rework the magic and you get P transpose beta hat. So P transpose here, not P hat. Sorry. P transpose. Very cool. And the reverse implication is quite nice as well, right? So reverse implication is nice as well. So let me do this here. For the reverse implication, you start with the fact that the least square has a unique solution, right? Estimate that P transpose beta unique. It means you take any two solutions, P transpose beta 1 hat is the same as P transpose beta hat. But that just means P transpose times beta 1 minus beta 2 hat is 0. That just means that if you take any vector in null space of X transpose X, P transpose lambda has to be 0. Otherwise, if it's not true, then you can produce a least square estimate to get the answer, right? So, very cool. Now, then once you have this, then P is orthogonal to lambda. P is orthogonal null space of X transpose X. That means P is in the row space. The row space of symmetry made same as column space. You get column space. You're done. Very cool. So that's the theorem we have shown today.